continue tying together some ideas. So hold on to those thoughts about the empirical rule. And we're going to add to that this definition or idea of z-scores. So definitely remember this formula. We're going to be using it a whole lot throughout the rest of the semester. So z-scores are telling us the distance of an observation from the mean. That should sound familiar, so let's work on our formula here. We're going to use the letter z to represent the formula. We're going to see how far an observation is from the mean. Kind of sounds like starting at a standard deviation almost, okay? But we're not going to square it or anything. How far the point is from the mean. And we're going to scale it in terms of the standard deviation. So we're going to divide by the standard deviation. And that's it. That's our formula. Box that. Make sure you know it. So this z-score, think about the order that we put the numerator in is very important. If the observation is above the mean, then this number will be bigger and we'll get a positive answer. So positive z-scores tell us the data point is above the mean. If we get negative values, that means our observation is smaller than the mean or below it, so negative z-scores indicate observations below the mean. And scaling by standard deviation is important. If we have a difference of 10, but we're talking about a scale of 10, then that's a really big difference. If we have a difference of 10, but we're talking about a scale in the thousands, it's not such a big difference. So we're kind of scaling this too, which gives us our first interesting property. This distance, remember our kids on the seesaw example, this distance from the mean, that would be in feet. You don't necessarily need to write this part down. Standard deviation in that example is also in feet. So check out what happens. The units cancel out. So first observation or note here is z-scores have no units. And this makes them really great for comparing items that are on different scales. And we'll see an example of that in just a moment. Now the second observation, if we're talking about z-scores on a bell curve, let's go back to our previous example for a second and calculate a z-score. What if we calculated the z-score for this guy? We have our observation of 32 minus the mean of 25. We're seeing how far away that observation is from the mean over the standard deviation of 3.5. Work that out for a second, and you should get 2. Okay, maybe something's starting to click. Let's try this one. If we did this z-score, we would get our observation is 18. We're going to see how far it is from the mean of 25. We're going to divide by our standard deviation of 3.5. And if you work that one out, you should get, excuse my pen here, should get -2. Okay, anything clicking? Notice to get 32, we added 2 standard deviations, so above the mean. So this is +2. We've added 2 standard deviations above the mean, and that gives us a z-score of 2. This guy, we subtracted 2 standard deviations from the mean, and that gave us a z-score of -2. So z-scores are really just counting how many standard deviations you are from the mean, and the plus or the minus part of it tells us, are we counting that many above average or below average? So thinking about it in this picture here, what kind of z-scores would we expect to indicate unusual observations? For example, would a z-score of 1/2 be unusual? So in our picture here, A z-score of 1/2 might be like right here. I've gone half a standard deviation. I would say that's not unusual. That's kind of with the bulk of the data right here in the middle. But as we go further out, they become less likely. Some places you'll see z-scores beyond 2 indicate unusual observations because there's only 2.5% of the data out there. That works for me. I'm going to go with the stricter definition of z-scores beyond plus or minus 3 are unusual because that's our about nothingness is out there. So let's jot a note down about that. I'll say z-scores beyond plus or minus 3 indicate highly unusual observations. Okay, and again, the reason is, in the bell curve, if we're talking about that setting, there's not much out there. So let's put this into practice with one example. So still talking about that Olympic data, now we're going to look at two different groups. We have male gymnast, so I'll just call this section G for that, and they tell us the average age for the male gymnast was about 23 years, and the standard deviation for male gymnast was 3 years. And we have a particular gymnast here who is 39 years old from Bulgaria that competed in the Olympics. So that's our observation of interest. Our 39-year-old gymnast from Bulgaria. Then we also have equestrians. I'll just label this E for equestrians. And they tell us that the equestrians, average age of male equestrians in the Olympics was about 40, with standard deviation 6.5. So for the equestrians, average age 40, standard deviation 6.5. And we have this observation. Hiroshi was 71 years old competing in the Olympics. That is pretty cool if you ask me. So 71-year-old competing in the Olympics for the equestrian events, 39-year-old competing in the Olympics for the gymnastics events. So our question is, which of these athletes is relatively older for their sport? Okay, clearly this guy is older for the equestrian event, just in terms of raw age, but relative to their sport is what we're curious about. So even though these are two very different distributions, one has a very low average age, one has a little bit higher average age, we want to compare on the same unitless scale. So that's what z-scores are very good at. So our z-score for the gymnast, his observation is 39, and the average for gymnast 23 over our standard deviation of 3. Again, the numerator, the order you put that in is very important. If you work that out, you should get 5.3 repeating. I'll just round it to 4 decimals as we're getting in the habit of doing here. And if I wanted to interpret this, I could say something like this. The gymnast is 5.333 standard deviations above average. And then think about, would this be an outlier based on the previous criteria we had? Absolutely. We said anything beyond 3 standard deviations is definitely an outlier. The percentage of observations out there is very low. This is beyond +3, and therefore a highly unusual observation. All right, let's check out our equestrian, see how he's doing. So our equestrian, the z-score, his observation is 71 years old, minus the average relative to sport is 40. A lot more variability in ages here, 6.5. If you work that out, you're going to get 4.7692. So this is telling us our equestrian is 4.7 standard deviations above the average. Say he is 4.7692 standard deviations above average. Again, this is more than 3 away, so definitely considered a highly unusual observation. So I'll make the same comment here. This is beyond +3, and therefore a highly unusual observation. So kind of to answer the last question here, which of these two athletes is older relative to their sport? Hopefully you're thinking the gymnast. His z-score, he is further above average for his sport. So even though he's younger overall, 39 versus 71, gymnasts have a very short career and they start off a lot younger. There's a lot more variability in equestrians with a much higher average age. So relative to the sport, the gymnast is the oldest because he is further above average for his sport. So I'll say the gymnast is older relative to his sport because his z-score is higher, meaning his age is further above average.